Good morning, everyone. Thank you for joining us on this webinar on precision timing with high-speed counters. It's roughly a 17-minute presentation, and if you have any questions, we can get to those afterwards.
Hello and welcome to today's webinar. Today we will be looking at precision timing using the Horner OCS High-Speed Counter. Let's look at our agenda for today. First, we will define what a high-speed counter is and when you should use one. We will do a quick review of the functionalities of the high-speed counters that are built into the Horner OCS. We will then identify today's application problem and plan and execute a solution. There will be demonstrations throughout, and we will finish with a Q&A session. Let's start by looking at what a high-speed counter function is. A high-speed counter is a special function of a PLC or OCS all-in-one controller that depends on special built-in hardware circuitry and allows some inputs and outputs to be processed outside of the logic scan of the PLC or OCS. This allows events that occur much faster than the controller scan rate to be handled accurately. The specific high-speed counter functionality for a PLC or OCS varies by controller. This means it is important to know the capabilities of your controller as you are planning out your application. There are a variety of situations in which you would need to use a high-speed counter function. For example, accurately counting pulses that are on for a short duration. They are also an important tool to accurately measure high frequencies. In today's demonstration, we will be using a high-speed counter to time an event where each millisecond is important. A high-speed counter is also needed to turn on a digital output when an encoder reaches a specific target position. In each of these examples, a high-speed counter is needed. This is because if the signals of these applications are wired to standard PLC inputs alone, it can cause signals to be missed or events to be inaccurately captured or triggered. In a previous demonstration, we measured the velocity of a pumpkin that was dropped from the roof of a building. In today's demonstration, we will measure the velocity of the pumpkin as it passed between point A and point B, where point A was the top of the roof and point B was the ground. As there was not a sensor attached directly to the pumpkin to measure this, we must get this measurement from photo eyes at the top of the roof and on the ground. To solve today's application problem without a high-speed counter, we would start by connecting photo eyes A and B as standard PLC inputs. Once photo input A turns on, we would start a 1 millisecond retentive timer. Then once photo input B turns on, the timer would stop. The accumulator value of the timer would then tell us how long this process took. This approach works best in scenarios where there is a large distance between photo points A and B and the object is moving slowly. As there wasn't a large distance between A and B in our demonstration and our object was moving quickly, we need a more accurate method to measure the elapsed time, so we will use a high-speed counter. Let's do a quick review of the high-speed counter functionalities of different OCS product lines. The XLE, XLT, and Micro OCS series have up to 4 high-speed counters available, including totalizing, frequency measurement, pulse measurement, and quadrature modes. Products in the XL series from the XL4 onwards, and including the X5, as well as the XL Prime series and future Canvas models also support higher frequencies and additional capabilities. These include high-resolution timing and flexible input triggers for disable, latch, preload, and clear. These models can also trigger outputs based on high-speed counter accumulator values. In today's demonstration, we will be solving a problem where precision timing is needed. For this, we will be using an EXLW controller, as it has a totalizer with a high-resolution timer and enhanced high-speed counting capabilities. Let's look at how we will set up the high-speed counter in our OCS for today's demonstration. We will be using the totalizer mode of the high-speed counter to count 10 MHz pulses generated by an internal clock. We will also wire photo eyes A and B into one of the 4 high-speed inputs in the OCS. These are labelled from H1 to H4 in the XL, XL Prime, and all future Canvas series. The high-speed counter will be counting in 10 MHz increments, and we will be using the photo eyes to capture and measure the elapsed time. There are 4 high-speed functions available to use for any high-speed counter application. These are disable, latch, preload, and clear. These functions can be performed by an external input connected to one of the high-speed inputs, or as an internal function triggered by a variable that's mapped to an internal memory point. Each function can also be disabled if not needed. The disable function prevents the high-speed counter from counting. The latch function takes the current value of the accumulator and copies it to a different location where it can be accessed later. The preload function sets the accumulator to a specific value, which is typically a non-zero value. The clear function clears the accumulator value to 0 when active. Let's look at some approaches to solving today's problem. First, let's look at an approach where we would mimic the PLC input method. With this approach, we would use the high-speed counter as a timer to start counting 10 MHz pulses when photo eye A is triggered and stop counting when photo eye B is triggered. To do this, we would have to connect the disable function to a physical input and then configure the function to turn off when the leading edge of photo eye A is triggered. However, the configure settings of the high-speed counter and disable function do not allow us enough flexibility to do this, so we will not use this approach. Now let's look at the approach we will use in today's demonstration. We will utilize the enable function internally in our program to enable our high-speed counter instead of using the disabled function or using an external input. We will assign the clear function to photo eye A and the latch function to photo eye B. When photo eye A is triggered, the clear function will reset the timer to 0 and start counting until photo eye B is triggered. Then the elapsed time in 10 MHz increments will be stored in the latch register, which we will then use for our calculation. To do this, we need to ensure both functions can be active on the leading edge of the switch, so that the clear and latch functions are carried out immediately when photo eyes A and B are triggered. In this screenshot, we can see how we would configure the high-speed counter to do this. The disable function has been assigned to an internal bit, which we can then map to a variable. The clear function has been assigned to our first high-speed counter input, H1, and the latch function has been assigned to our second high-speed counter input, H2. Both functions have then been assigned to be active on the rising edge of the signal. Once we have configured our high-speed counter, we need to create variables to use in our program. To do this, we will first go to the user manual of our controller and find the high-speed counter memory map. Here we can see the memory map for the EXLW counter 1 with the memory map for the accumulator and latch value, which are mapped to %API registers, and the memory map for the latch, preload, clear, and disable functions, which are mapped to %queues. Our latch value is where our resultant elapsed time, measured in 10 MHz increments, will be stored. We will create a variable for this as a double integer that we map to AI403. We will also create a variable for the high-speed counter disable function, which we will map to Q1604. We do not need to assign variables to the latch, preload, or clear queue bits. Finally, we will create variables for photo eyes A and B so that we are able to check their status. We will map those variables into I9 and I10. This does not impact the operation of the high-speed counter. Once we have the elapsed time, we can calculate the velocity. First, to convert our elapsed time, which was recorded in 10 MHz increments, to milliseconds, we divide the value by 10,000. To find the velocity in inches per second, we divide the fixed distance between photo eyes A and B by the elapsed time multiplied by 1,000 to convert our milliseconds to seconds. To then convert this velocity to miles per hour, we can divide our velocity in inches per second by 17.6. Let's look at our bench setup for this demonstration. On the right, we have an EXLW OCS, which is running our Pumpkinator 5000 program. On the left, we have an iOS simulator wired to the first two switches. Switch 1 is connected to the first high-speed input and is acting as the clear function. Switch 2 is connected to the second high-speed input and is acting as the latch function. Now let's look at our program in Cscape. First, we will look at the I/O configuration. To look at the setup for our high-speed counter, we will select Local I/O, then Config, then Module Setup, and then Digital In/High-Speed Counter. Here we can choose our counter mode, and we can configure whether our inputs are positive logic or negative logic. Below this is the standard memory map for the different high-speed counter functions. These can usually be left as default. There are also filter capabilities which can be used to prevent signal bouncing on the photo eyes, but we will not be changing these for today's demonstration. Finally, we have the options to configure our high-speed counter. In today's demonstration, we are using the totalizer mode of the counter. We are also using an internal mode, which is counting clock pulses in 10 MHz increments. Next, we can decide where we want our disable, latch, preload, and clear functions to come from. We will be using our disable function as an internal variable. We will then connect our clear and latch functions to external high-speed inputs 1 and 2 respectively. We will also ensure that these functions will be acting on the rising edge of these signals. Next, we will look at the program variable table and see the variables we have created for this demonstration. First, we have our high-speed counter disable function, which we chose to be an internal variable. We have created a Boolean variable for this, which we have mapped to Q1604. This is the default memory address for the internal disable in the high-speed counter chapter of the EXLW user's manual. We have also created an unsigned double integer variable for the accumulator, which we have mapped to AI401. Then we made the key latch variable mapped at AI403, where our elapsed time value is going to reside. Finally, we have created two variables for our photo eyes so we can view their status. We have assigned %I9 and %I10 for these. Now we will return to our bench setup. First, we will enable our test, which will turn off the disabled function to the high-speed counter. We will do this from the OCS screen. Now our test has started. Our object will reach point A when we flip switch 1, and then reach point B when we flip switch 2. Here we can see that the elapsed time between flipping both switches was calculated to be 2.75 miles per hour. In our program, we can also look at our test in further detail. Here we can see the drop height, which is the distance between points A and B. Here we can also see the values from our previous trial for the accumulator and latch value, as well as the results of our calculations. If we start a new trial by enabling the high-speed counter from the OCS screen, we can see that the accumulator value starts increasing without clearing and resetting to 0. Now let's trigger photo eyes A and B again by flipping the switches. Here we can see that our accumulator value increased until the high-speed counter was disabled. However, our latch value, which is in 10 MHz increments, stopped when photo IB was triggered. This is why our accumulator value is different than our latch value here. If we depended on freezing our accumulator through a real-world logic input, our results would not have been accurate and would have been off by a few counts. Let's run another trial by first enabling our high-speed counter. Once again, our accumulator starts from the point stopped at in the previous trial. Then we will flip our two switches. Now we can see that our accumulator and latch value are the same. This is because the second switch bounced. This can be prevented by filtering the high-speed counter. Let's look at how we implemented the logic for the high-speed counter in Cscape. On the first scan of the controller, we turned on the high-speed counter disable function. The high-speed counter on the first scan is frozen at its previous value. On our next rung, when our high-speed counter disable function is turned off, we have a negative transition one-shot that will turn on and indicate the start of a new test. Once we start a new test, our previous calculations will be cleared and an internal flag will be set to show that our test is now active. Once our test is active and photo IA is tripped, we set another flag that shows that our test has started and that our object is between points A and B. Once photo IB is tripped, our test is complete, and we should have a new result in our latch value. When our new result one-shot hits, we will do our calculation to take our latch value as a double integer and convert this to a real value. This will then be divided by 10,000 to get a millisecond value for the elapsed time. We will then take the elapsed time to calculate the inches per second and mile per hour. Once we have done our calculations, we will clear all our flags and disable the high-speed counter again, and we're ready to start a new trial. That concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, hopefully that was of use to you. I'm not seeing anything in on it just yet. We are on again in 2 weeks' time in the same slot. If you do wish to see what webinars are coming up, you can go to the website under support and webinars, and we will have the list of the next 3 upcoming webinars. Okay, other than that, I think that covers everything. There's no questions in, so have a good day and we'll see you next time.